Let's talk matter, pure substances and mixtures. So what exactly is matter? Well, it is anything that has mass and volume. So matter is composed of atoms, but remember, atoms are too small to be seen with your eyes. So if you look, here's just some things to help you get a scale of how small an atom is. You should have just a reference of how big a centimeter is, right? And so let's add commas just so we can see what this number is. So we could fit 100 million atoms lined up in a centimeter. All right, so here's the classification of matter. Matter is either a pure substance or a mixture. So remember, matter, anything that has mass or volume, and it is either a pure substance or a mixture. If it is a pure substance, it is either an element or a compound. If it is a mixture, it is either a homogeneous mixture or a heterogeneous mixture. All right, so we're going to look at pure substances first. What is a pure substance? Well, a pure substance is only one kind of particle, and it cannot be separated physically, okay? It has definite properties, things like melting point, boiling point, density. It has chemical properties like, is it flammable? What does it react with? What is its half-life? Okay, some of those properties can be used for identification. And you can see as an example, some of these are elements like gold, some are compounds like sugar, but they are all pure substances. So let's focus on elements first. So elements are a kind of pure substance, and a pure substance is a kind of matter. So what are elements? Well, elements are pure substances. They have unique properties. All atoms of the same element have the same number of protons. Okay, so look, hydrogen, atomic number 1, number of protons 1. Carbon, atomic number 6, number of protons 6. Sodium, atomic number 11, number of protons 11. Okay, it has a unique chemical symbol, hydrogen, helium, lithium, and so on. It cannot be separated physically or chemically. Elements just can't be broken down, okay? Here is our periodic table of elements. Okay, so you do not have to memorize symbols. If you want to find the names in our reference table, you got to flip to table S and you can see the names, but it is not a memorization thing. And here on our reference table is where we find the atomic number, the number of protons. Now, element chemical symbol examples. So element symbols begin with a capital letter always and only have one capital letter. If they have other letters, they must be in lowercase. Okay, so hydrogen has one letter, perfect, capital. Helium has two letters, first one capital, second one not. Okay, a very common one to make an error on is Cl. There is no Ci at all, okay? And this is often mistaken. If it was an I, it would look like that with a lowercase, but this just doesn't exist. All right, element. Some are monatomic, which means they exist as single atoms. And those fairly exclusively are the noble gases found in group 18 of the periodic table. And here you can see an example of a monatomic element where we just have a single atom existing. But atoms can also be diatomic. Okay? Some are diatomic and they exist as a molecule of two bonded atoms. Now, the elements that you have to know that are diatomic use the phrase Brinkelhoff. So look at this. Brinkelhoff. Okay, so that's a way to kind of keep that in your head. So here you can see, how do I know it's diatomic? I have two atoms of the same element right here bonded together. Now, something else that's kind of a little bit interesting about atoms is allotropes. Now, allotropes are different forms of the same element. So those forms, they're the same element, but they have a different structure, which gives them different properties. So for example, diamond and graphite are both forms of carbon, but they obviously have ridiculously different properties. Graphite is used in pencils, very soft. Diamond, hardest substance on Earth, can scratch glass, but they are both forms of carbon. So we call them allotropes, forms of the same element with different structures and different properties. Okay, another example of allotropes, well, that would be oxygen. So two very common forms of oxygen are O2, oxygen gas that we breathe in and use for our life processes, and ozone, O3, which instead of having two oxygens bonded together has three, and this has very different properties. So allotropes, same element, different properties. All right, now we are moving on to compounds. So right here, a compound is a pure substance, and a pure substance is a type of matter. So again, a compound is a pure substance. It has unique properties, but here's where we get some differences. They're composed of more than one kind of atom. They have a unique chemical formula instead of just a unique symbol. They have a definite composition, meaning if it's water, its formula is H2O, always, 100% of the time. And it cannot be separated physically, but it can be separated chemically. So in water, for example, H2O, the hydrogen and the oxygen are chemically bonded, so we can chemically separate them. One way that we can chemically separate compounds is with a process called electrolysis, where we use electrical energy to separate substances into their component elements. For example, separating water into hydrogen and oxygen. Now, there are many types of formulas and models. Let's go through some. So molecular formula lists exactly the number and type of each atom in the formula. So glucose, for example, has 6 carbons, 12 hydrogens, and 6 oxygens. Octane has 8 carbons and 18 hydrogens. We also have empirical formula. So that's when you take the molecular formula and reduce it to the simplest whole number ratio. So if I look at this formula right here, the ratio of carbon to hydrogen is 2 to 6. But what could I reduce that to? Well, I could divide each of those numbers by 2, and I would get CH3. I don't write the 1, even though I know when I divide 2 divided by 2, I get 1. So look at the next one. I have C4, H8, right? And I can this time divide by 4, so I get CH2. Now next I have C6 to H12 to O6, okay? What do I get with the empirical formula? Yeah, so I can divide by 6 this time. Now we have structural formulas. With structural formulas, I use my eyeballs and I count. What do I see? When I write a structural formula, I'm going to use the order of this, CHO, and then anything else that I have, okay? So I'm going to count. Look, I have 1, 2 C's, right? So C2, 1, 2, 3, 4, 4 H's, right? and 1, 2 O's. So you see, if I'm doing this on the exam, I'm really counting real careful, right? Crossing them out. And then when I look at the next one, I do the same thing. So what do you get for this one? Yeah, C2, H6, O. All right, then the ball and stick model is what we make with the model kit. So it actually shows the number and type of atoms, how they're connected, and it gives us a little bit better representation of the three-dimensional structure. All right, now let's go to mixtures, okay? So again, we looked at pure substances already, right? And we had compounds and elements, but now we're going to be focusing on the mixture side, okay? And this chart, if you want to come back to it, is kind of a great way to see the differences between the types of matter. Okay, so it's just a question thread. So can the matter be separated physically? If yes, it's a mixture. If no, it's a pure substance. Can it be broken down chemically? If no, it's an element. If yes, it's a compound. Okay, so it gives a great flow chart for you to use as a reference. Again, we are going to be focusing here on mixtures, which are a type of matter. So what is a mixture? Well, it's two or more pure substances physically combined. So that's why we had to learn pure substances first, because now with mixture, we're combining them. Now, it has a varied composition and varied properties. What does that mean? Well, you can have salt water. So salt, whatever salt it is, let's just say it's NaCl, and water, H2O. Combine them, you have salt water. Okay, but you can have water that's saltier than other water, right? So you can have, as you can see a representation here, you can have it stronger or weaker, more concentrated, less concentrated, okay? With a mixture, the components of the mixtures keep their properties. So again, if we're talking about salt water, the salt is still salt and the water is still water. I can actually separate them, and they do not change their properties. So if I mix sulfur and iron filings, the sulfur does not become magnetic, the iron stays magnetic. Okay, and I can use their differences in physical properties to separate them, which we'll get to. So homogeneous mixture. So here we are, type of mixture, which is a type of matter. In homogeneous mixtures, the pure substances are distributed uniformly, and actually they don't look like separate things, okay, like sweet tea or salt water or 14 karat gold, for example. So any two samples from the same mixture have the same properties, okay? So if it has been mixed correctly and it is a homogeneous mixture, then all of the samples are the same, okay, same properties. Then what about heterogeneous mixtures? Again, a type of mixture, which is a type of matter. Here, the pure substances are not distributed uniformly. I can see the different parts of it. So like smog or sand with water, soil, oil and water, orange juice, you got to shake it up, okay? Two samples from the same mixture may have different properties. So for example, when I make a salad, every two bites are not identical. One might have more lettuce or more dressing, or one has a crouton or a piece of tomato and a cucumber, whatever. So the samples are not identical because the things weren't mixed completely. Okay, it's like if you make Kool-Aid and you don't stir it up, the top part is going to be terribly unsweetened. And then when you get to the bottom where all the sugar is going to be exceptionally sweet. So the samples from the same mixture don't have the same properties. All right, I've already mentioned it a little bit, but we use physical properties to separate mixtures. So a real basic one is decanting, which I just like to call careful pouring. So basically what you do here is, and typically use a stirring rod, and pour the liquid, which has a solid visible in it, along that glass rod. And you can pour off the liquid and keep the sediment, keep the solid inside the other beaker. Not a super precise way, but possible. Now, when we're talking about the ones we're usually tested on that you really need to remember, here's one, filtration. So this is a separation based on particle size. So some things pass through the filter paper and others don't. So typically we use this when we have something that doesn't dissolve in the liquid. So we pour it through, the liquid goes through, okay? And then the solid pieces remain on the filter paper. Now, if I have something dissolved in the liquid, like if I have salt water, okay, and I pour it through, the salt water is just going to go through. Okay, so if I have salt, water, and sand all mixed together, I could pour the mixture through filter paper, trap the sand, and then what would go through would be the salt and the water. So that would be one step towards separating. So then I would need evaporation. So evaporation is a technique that can be used to separate a dissolved solid from a liquid. The liquid evaporates and leaves the solid behind. You can just leave it out at room temperature. The water will slowly evaporate. If you heat it up, though, it happens faster. Now, another type is distillation, and this separates liquids based on their differences in boiling point. So what do I mean? Here I have a mixture, for example, right here, and I have two liquids, and say one boils at 50 degrees Celsius. So here I have my thermometer, right? I'm going to heat this up to 50 degrees Celsius. That liquid will start boiling, the gas will rise up here and then condense to a liquid and be collected over here. And then the other liquid will remain. Okay, now if I had a third liquid in there, and say I have a boiling point of 80 degrees Celsius for that one, and what's left is water, okay, once I'm sure all of the boiling has stopped at 50 degrees Celsius, I've collected all of that liquid, then I can replace this flask right here with a new one, raise the temperature to 80 degrees, collect that next liquid, and then I should have my 50 degrees Celsius boiling point liquid, my 80 degrees Celsius boiling point liquid, and what is left here should be my 100 degrees Celsius boiling liquid. Okay, so distillation is a way to separate based on boiling point. And then we have chromatography, and chromatography is a way to separate based on size, meaning big molecules don't travel as far up the paper. Okay, so it goes up like this. Big molecules don't travel as far. Solubility, so if something is soluble, if this solvent that I have, the liquid here, is water, and it's soluble in water, it's going to kind of be stuck to the water and go with it, okay? And then polarity, meaning are the molecules in the dye more attracted to the paper or to the solvent? Okay, so all of those things can play a role on what happens when I see the results from my chromatography experiment. And it's chroma, so it's typically used with colors. A very simple way is to use a magnet. Like we said, when we mix sulfur and iron filings, we can separate what is magnetic and what is not. Whew, that was a review of matter, pure substances, mixtures, and then separating mixtures.